Last time we talked about AC. I actually said that it was actually easier to make current in AC because I made the example about the heating up process makes a magnet rotate and produces AC. For instance, you can have also a dam. I made the example of the dam, and which is still gonna make magnets rotate and produce AC and so on. But I said that a solar panel was different because it was going to produce DC current. So now I'm going to show you how it works since I promised that I was going to show you. In order to get the solar panel, we're going to need sand, which has to go through a very, very specific process because it is going to have to be converted into 99.9% silicon. So, how is it done? Well, the sand plus carbon goes through a process of 2000 degree and gets the raw silicon, which then can mix with hydrogen and gives us something like a gaseous silicon. Now, from this gaseous silicon, we can get a polycrystalline silicon. And then H2, which is a polycrystalline silicon, which then gets it gets cut into slices and it gives origin to wafers, which are basically the heart of the solar panels. Now, what is a solar panel? Well, a solar panel, which is an object like, I'm gonna try not to screw up the drawing too much. Yeah. Okay, so let's suppose that this is my solar panel. Inside here we have single cells, and inside every cell are two bus bars. So if we had to look at one single cell, we will see that this cell has two bus bar. Those cells are connected in series and all these are connected in parallel. So we have a series plus parallel connection. Through the bus bar. So, because a single cell will produce something like 0.5 volts, very modest. So we have a combination of series and parallel connection to the bus bar. Now, how do they work though? Well, we have here, if we're gonna see the layer inside here, we will see basically two layers. I'm gonna draw them as layer 1 and layer 2. Okay, so this is gonna be my layer 1, this is gonna be my layer 2. Now, in here, we have the polycrystalline silicon, so it's like pure, very, very pure silicon. And in order for this to be used, silicon actually has no free electrons. So we know from our, very, very first video, and from all the exercises we have been doing, we know that current is the flow of electrons, and electrons, in order to move, have to have they have to be easy. They have to have a loose electron in the very last electronic level. For instance, I in the very first video I've been talking about copper, which has 29 electrons and only one in the very last electronic level. So it's going to be easy for it to lose that electron. But in silicon, there are no free electrons, so silicon is not gonna not gonna let the electron is not gonna let the electron move freely, easily. So what do? Well, we do something that is called doping. So if I dope this side with phosphorus atoms, so this side is doped with phosphorus atoms, which have 5 valence electrons. Then one electron is going to be free to move because they have 5 valence electrons. So one electron is gonna be free to move. This is called n-type doping. Now, in the lower part, we're gonna do something similar, which is called p-type doping. We're gonna do the same, but we're gonna use boron. So if we doped with boron, so we use boron to dope these other ends. Boron basically has 3 valence electron. So we're gonna have one hole because one is gonna be missing and is gonna accept electrons from other atom. So we're gonna have one hole for each item. Now, what's going to happen? Well, we are basically going to have something that is called let me just put it in red. Whoops. Something that is called a depletion region. In which there are no free electrons or holes, and we're basically gonna have on this side, because those doped with phosphorus are gonna be attracted by those doped with boron, and there is going to be a depletion region in which there are no free electrons or holes because of this attraction. Now, what happens when there is light and light strikes the photovoltaic cell? Okay, let's suppose we have the sun and there is light, so basically photons. Well, sorry, what photons get here and penetrate through the depletion region, there's going to be something very interesting is going to happen. There's going to be they're gonna form, well, those photons are gonna give energy to this, and we're basically gonna have all the atoms with one electron on one side, and the atoms with the hole on the opposite side. And there's going to be a potential difference, a huge potential difference across those two. And in the depletion region, there will be an electric field formed. However, those one cannot reach those other one. They would like to reach them, but they can't because of the depletion region. So what happens? Well, as we connect them through here, through some load like an empty battery, okay, this is gonna be my battery, my empty battery, well, then those electrons are gonna try to reach the holes. So these electrons are gonna go through the battery trying to reach the holes. In this sense, a photovoltaic cell is gonna give us DC current. So every time you see a DC cell, a photovoltaic cell, you gotta think that it's gonna give us DC current, and it's the only one. Well, not the only one, but probably one of the most used one, which gives us DC current, as opposite to all the other one, which are gonna give us AC current instead. So yeah. This is basically what happens inside a solar panel or a photovoltaic panel, depending on how picky is your processor with the terms. Anyway, yeah, this is pretty much it.